not see they are boring, they are beautiful, but I think it's more exciting to see the mathematical action. So what's the capacities of the deep Gaussian process simulation? So we'll start with Gaussian process simulation. So you can think it as a very flexible black box mathematical tools that tries to mimic the functional behaviors of the any computer simulators. It's just try to understand how a computer simulator works by learning the patterns from its input and output. So you can see it's as a black box model. Essentially, it's a bunch of the mathematical equations. So this is a Gaussian process. We use it for the emulation. There are also, of course, other candidates for emulation. You can use neural network or other approaches, polynomial chaos, but we prefer Gaussian process because it provides native uncertainty quantifications. And with Gaussian process, we have a suite of the other tools that can help us to do, for example, optimization, calibration, etc. And so the deep Gaussian process simulation, as you see, it's just a network of the Gaussian processes. It's a straightforward network. It provides more expressive class of surrogate models. If you see this network of Gaussian processes, you will see immediately that it will take more computational time to construct such one because there are latent layers introduced by this network. But also you will see we not actually able to mimic models without multiple output. And we'll talk more about this and how that will facilitate other models where you might see stochastic behaviors in it. So why deep Gaussian processor rather than a simple GP, which is more computationally cheap? So here I draw some of the samples from Gaussian process and the basic three layers of the deep Gaussian process simulation. I just see for the simple GP ones, you have very stationary global trends, very smooth ones. While with multiple layers, you are able to simulate some of local variations like here and here, and they have these very long stationary behaviors. So that's the reason why we want to use a deep Gaussian process because they're able to mimic some of the complex behaviors of the computational model. I will showcase with a very simple synthetic example to see how deep Gaussian process could help to emulate this particular synthetic 1D example where you see very quiet region and regions where you have rough up and downs. We try to emulate this true function by sampling from it. Well, in reality, you won't observe the whole underlying true function. Instead, we can only sample from it and trying to sample more data points in order to replicate its behavior. So if we sample adaptively, starting from 5 simulations from it, and you will see after 100 simulations, it somehow achieved 5.2% of error, but most of the computational efforts over this very flat region, which you will see as a waste of the time and computational resources. And you will see because of the stationary assumption of the GP, you have very high uncertainties over here because it basically maps the uncertainties due to the stationarity because it measures the uncertainty based on the distances between the data points. So that's not good because from the uncertainty, you won't tell, okay, we actually achieve a very good prediction over here. Well, we want more data points and we should be more conscious about the predictions over this rough region. And if we switch that to the deep Gaussian process. Here I pick a 3-layer one. You can use 2-layered as well. And start exactly the same initial simulation, which gives you 20% of initial area. And start sampling. Let's also sample 100 simulation. You see most of the samples over this rough region, well, on this very flat region, you only have at most, I think, 10 points out of 1,000. Then you can choose much lower areas. So that's the reason why we want deep Gaussian process, because it can distribute your computational efforts based on the function complexity of the underlying computer models. And the uncertainty is much better. So you see in this very quiet region have very low uncertainties. So that basically help to direct the regions of your computer model simulation in order to improve the performance of the emulator. So that's the first aspect I want to discuss. That's just first safety of the deep Gaussian simulation. The next thing I want to discuss is the scalability. I think the further details will be shared by Brian. But here I just showcase how we can scale the deep Gaussian simulation so that it can adapt to a lot big data. So what I mean, the big data is not like millions, probably tens or thousands of hundreds of data sets. Here I just use this two-dimensional synthetic example because it's basically very non-stationary to showcase how we can make our deep Gaussian simulation scaled. So in left-hand side in this figure, I run GP with the GP Vikia, so it's approximated Gaussian process scaled with the dataset, and also the DGP and DGP Vikia. So you see if I run a full inference of this deep Gaussian process emulation with, I think it's 200 or 300 data points with a single iteration. No, I think by running 200 iterations of the training, it spends like 7 minutes to finish. So you basically, I won't be that patient to wait for like an hour to wait to finish. But if you use the Wiki approximation with a similar amount of time, you can scale it to like 10,000. So that's and that is on I think it's on a 8-core processor. So if I have more cores, that it will achieve lower computational time to deal with 10,000. Of course, GP and GP Wikia is fast because it only deals with a simple input output with no latent layers to be inferred. But the downside is that if you see the right hand side, especially if you have relatively moderate number of the data points, the deep Gaussian process can achieve much lower. It's on the log scale, so you should expect a huge difference between the models. So you can expect lower areas by using the deep Gaussian process. Of course, if in this simple 2D example, you have 10,000 that basically covers the whole function. So the overall errors won't be very different between GP and DGP. So that's the scalability. Next is connectivity. So the deep Gaussian process is not just used for single simulator. If you have a network of simulators, or if you have a simulator that can be decomposed into sub-processes where you can observe the internal in and out, you can actually achieve a divide-conquer strategy to achieve a better emulation. So if you have a network of the sub-processes, you can emulate individual processes independently and then connect them together to form overall emulator. So that's we call it a deep Gaussian process simulation. The inference of it actually is straightforward if you see it just as a deep Gaussian process emulator with partially latent layers. And I will show this exact example to see how this linked approach can help to improve the performance of the emulation. So you've seen this synthetic 1D example before, where we use a GP and deep Gaussian process to emulate its behavior. So if we know that this is simple composition of the three faithful connected subprocesses, then we can emulate these simpler functions individually and connect them together. So I sample also 5 initial simulations from these individual subprocesses. The computational time is the same as you sample from this composed simulator. But instead of learning from this point and sample from the whole simulator, you try to extract the internal in and out in this network. And you will see that after 100 simulations, you can already achieve below 0.1% of error. And that's all because the decomposed process are much easier to emulate it. And you can do the emulation individually and connect the emulator directly rather than the physical processes. It's much easier because it's all GP or deep Gaussian process simulations, and we enable closed form connection among them. So that's fast to evaluate. So we can use this linked deep Gaussian process simulation in the Joule's time series prediction. The details will be shared by Minda tomorrow. But here I just briefly talk through the idea. So this is Joule's. The input is just a bunch of the climate time series and the outputs of each carbon time series. If you think about the mechanism of the Joule simulation, it basically simulates the carbon storage at every time step. So what we can do is to treat every time step in and out as a single emulator. And then basically this time series can be emulated or represented by going through these circles. So you initiate at a certain point of time, and a single emulator produce the carbon storage at next time step, and that fits into another emulator. So that emulator can be the same if you assume that each time step in the joules follow the same mechanism. So it goes through these circles multiple times, and you will get something like this. So the red line are 2 joules result, and these black lines are a result produced by the linked emulator. So basically it goes through the circles, and that will produce this output and along with the uncertainties. So that's how to utilize the linked deep Gaussian process to emulate the time series. The next aspect I want to discuss is dimensionality. It's not a model about trees. It's a model that I work with Alex. But I thought it's very interesting and novel application of this. And there might be some models in the net zero universe that mimic this structure. So this is a primary simulator. So this is known as divided into multiple compartments, about like compartments, and each compartment has several features that is specified by the threshold opening pressure, extinct pressure, and the stiffness index. And And there are 100 compartments, and each of them have these three different values. So in total, we actually have 300 dimensions. And overall, you will get a single scalar output, which is a partial pressure of carbon dioxide. So this is a very tough problem because you have very high dimension. You need the 300 different values to produce a single value. So if you want to achieve very good emulator for this pulmonary simulator, you potentially need a lot of runs. And because of the high dimensional nature of the simulator, you are unlikely to get a very sensible or good performed emulator. As you see here, I use the scalable Gaussian process version um, to emulate the three-dimensional simulator with almost 20,000 simulations for it. It takes several hours to finish. But you see that the predictions, this outsample prediction, I think I predict over 10,000 of the testing points. It's nowhere near the diagonal line. And also the uncertainties are uniformly high. So you can basically, if you don't know the underlying truth, you cannot measure um, the accuracy of the predictions by checking the uncertainties. They're all high. So you can safely assume that's all poor predictions. So a way to improve, of course, is to reduce the input dimension. If you reduce input dimension, you have a hope to improve the performance and lower the uncertainty. So here I use this Mars idea that I think Muhammad will talk about in more details to reduce the dimension. But in this case, you see here I plot the ratio variance of basis, just variance of the eigenvalues. I can reduce it from 300 to around 100, and then just choose the first three leading principles and then refit my scalable GP. And you see it improved a bit. It's more or less along this vertical line, but still you see the uncertainty is not very satisfactory. And the mean prediction area is still over 10%. So this gives the impression that whether we actually can find a very good active substrates to increase the sets to improve the overall performance. So are there any other ways to do the same emulation but with better uncertainty quantification and lower areas? And if you have more simulations, you have sort of guarantees to lower the area. So we can globally convert this problem into a network problem. So you don't really need to do any dimension reduction. You just decouple this model into a network. And in this network, the individual components are no dimensional. So that's much easier to handle. So here I decompose this model into a four-layered network. In the first layer, you have identical five-dimensional emulators. Basically, you treat each compartment as a single computer model, and you try to construct a three-dimensional deep Gaussian simulator of that. And the output, you can group them. Every five output of these compartments can be grouped to produce the partial carbon dioxide pressure. And so in this way, of course, it involves sort of the experimental design. I don't think I have time to talk through of them, but all these latent layers can be simulated from the original model by doing a good experimental design. But overall, if you just see the input and output, it's still 300 dimensional input and the scalar output. But internally, you are actually dealing with much smaller dimensional subprocesses. And by doing this, you can achieve much lower areas. You can achieve like with the exact same number of simulations, you can achieve 5% errors, and you definitely can see the uncertainty improves a lot. And if you make more simulations, we have sort of guarantees that you are able to achieve lower errors, because now you're basically constructing very low dimensional emulators without any dimensional reduction. So if you increase the number of the simulations, you basically can improve the emulators for each either it's 3 dimensional or 5 dimensional, and you just need to connect them to achieve this overall emulation. So that's different ways to deal with the dimensionality given the nature of this computer model, which is a compartment model, and on each compartment you have a smaller dimensional input. And finally, I want to discuss this stochasticity of the deep Gaussian process. This is a recent development of the approach. So I understand most of the models will deal with a deterministic. So if you evaluate the model at a given input, you won't get different output. But there might be models where you might have different scenarios or some randomness embedded, so you will have different outputs. And of course, it depends on how you assume the distribution of your output. So you can cast different distributions to model the output. And to incorporate this stochasticity in the deep Gaussian process simulation framework is actually quite straightforward. As we see that before, the deep Gaussian process actually can handle multiple output. So this multiple output can be used to control the model parameters the model parameters of the different distributions. You can assume any parametric distributions, and this deep Gaussian process just tries to control how these distributional parameters change when your input changes. So I call this L as a likelihood layer. Basically, can represent any parametric distribution that you choose. So here I create a very simple synthetic simulator, which will where here I think I simulate 40,000 simulations from this very simple 1D example, and it was simulated over 800 unique input locations. At each location, I have 50 replicates, and you will see these two here. And if I want to mimic this stochastic simulator, what I need to do is to construct this deep Gaussian process hierarchy. So these two GPs basically controls the mean and the variance of this simulator, and this Y is your observation. This is that point. If you train this, the training is straightforward. It's also forcing or stochastic imputation inference. This red solid line is a mean prediction, and this dashed red line upper and lower uncertainty bounds. And here I just want to show you the time scalability of our approach. So if you just feed this 40,000 data points into the inference, a single iteration of training takes more than 10 minutes. Actually, my RAM just cannot feed this 40,000 by 40,000 metrics. But we can do better. by using some mathematical tricks and derivations to scale this inference to the unique location. So that leads to 800 by 800 metrics. So that takes less time to train. And we can also utilize a Wiki approximation to make it even faster. So that scales with the number of the condition points. So you see, if we use this approximation, one single iteration takes 9 seconds. So that's a bit about scalability. And these are the true mean and variance functions used to simulate this state point. And you see, we can infer these two functions quite nicely with our inference approach. You see, we can actually capture this slight deep and up and down trend of the second order information. And finally, very quickly, so this is epidemic model, which in fact are a number of the infected population. So in most of the literature, see when you try to emulate these outputs, you assume these outputs are actually Gaussian distributed. So if you use the heteroscedastic Gaussian, you will see the issue that you might have predictions at negative numbers, which is not true. So with our inference approach, because you can choose any parametric models distribution like, you can use negative binomial and you are able to choose much better emulation results. You stay on the positive phase, and because of the negative binomial, you can model the mean and the variance as well. And of course, this is just one case about using this stochasticity. You can pick other models distributions based on your assumption on your data if we have multiple regions. Okay, finally, all these examples can be run using our DGPSI package that I can download from the GitHub or Chrome. That's it.
Oh.